Yeah, I know.
It's scary. Because they just know, like, oh, statistically, this is going to happen.
I don't trust them.
No, neither do I.
Don't trust them. Don't like it. Yeah.
I will learn them and manipulate them.
So lecture 6.2,
Here we go.
measuring resistance well. Okay. Many sensors are resistive. So this is our motivation. So many sensors are resistive sensors, meaning the physical quantity to which they are sensitive affects the electrical resistance of the sensor. The accurate measurement of which is necessary for an accurate measurement of the physical quantity. So an example would be the thermistors that you guys used in the lab, the thermal modeling response lab. Remember that? Where you used a resistor to heat up a block of something and you measured the temperature? Sound familiar? Do you guys go here?
Yes.
I mean, it would have been nice to have this lecture before.
So, did you take that lab like last year? Oh, you're taking it right now.
Remember, I can take that lab last year. The same reason I can take this class last year because I needed vector calculus.
Which
For
now you
some
don't
weird reason.
Guess what? Guess what? We're gonna do partial derivatives today.
You're gonna do them.
Oh,
For you. For you.
I learned that in DiffyQ.
Oh. I think we actually are getting rid of that prerequisite. So, no, getting rid of vector as a prereq for this class. Okay. Anyhow, so resistive sensors are important, like the thermistor, but there are many types. There are there are light-sensitive resistors. There are all kinds of resistive sensors. So measuring resistance is really important, not just for what is the resistance of this resistor, but as a measurement technique for a sensor. So in lecture 6.1, we learned that we can measure unknown resistance, Ru, by applying a known voltage to it, Vs, measuring the current through it, IRU, the unknown, so the current we're going to measure through it of the resistor U, and using Ohm's law, we can say that Ru is equal to Vs divided by IRU. So Ohm's law pretty much just directly applied there, and we can measure the resistance that way. That's great. So if you measure the voltage, you measure the current, maybe using like a Hall effect sensor or something, you can measure you could back out the resistance. Another way that we mentioned is to place the unknown resistor in a voltage divider circuit with a known resistance, Rk, apply a known voltage, Vs, measure the output voltage, Vrk, and use the voltage divider equation to give us, so the voltage divider equation is Vrk, as I'm confident you remember, Rk divided by Rk plus Ru times Vs. So a voltage divider circuit always has that. So we use the voltage divider equation to solve for the unknown resistance. So the unknown resistance is Ru. So we know Rk, it's a known resistance. We measure Vrk, and we measure / know what the input voltage is. So solving for Ru in this gives Ru ready to rumble, Rk Vs divided by Vrk minus 1.
So is that all in the denominator, or is that fraction?
No, so that ends right there. I guess I could put the parentheses to be very explicit like that. You're right to call out that as ambiguous, though. So,
MATLAB knew what you were talking about.
MATLAB, yes. MATLAB would know. Okay, so this is our resistor value. So we would have to measure 3 things instead of 2. So up here we had to measure voltage and current. Here we have to measure 3 things, 2 voltages and a resistance, right? Good. And these actually, people will use these methods. It's not that these are totally unused methods. These are both used methods, but they both share this sort of issue with them. And this is why we're going to learn the Wheatstone Bridge. So the sensitivity of these methods to measured quantities IRU and VRK are, and here come the partials, partial of RU with respect to IRU equals, so if I came back up here, took the partial of RU with respect to IRU, I'm confident we could all do that derivative. Negative Vs divided by RU squared. So that's the sensitivity for the case where we measure the current and the voltage to back out what the resistance is. And in the other case, we have dRU dVRK. And so that's this expression here. If you take that derivative, you get negative RK divided by VRK squared. Oh wait, I missed a VS in there. Well, that doesn't seem right. There was a VS before the divided by. RK VS over VRK squared. Now, for small IRU or VRK, which correspond to large RU, these are very sensitive, okay? So if you change the current just a little bit, the resistance, so if you're down, say like you're only flowing like 2 milliamps of current, then your sensitivity is, so maybe you're applying 5 volts or something. Your sensitivity is 5 divided by 0.002 squared. Big. A lot of 5s there. A lot of numbers. So.
That is.
That was also a 3.
It was also a 3, but we're not gonna talk about
Oh yeah, it was, wasn't it?
it. It could. It actually did.
You
We-
never know till you try.
1.25 million.
Fives.
Million.
Big number.
So that means that the slope
By a factor of 5.
the slope is really freaking huge there, right? And that's not great news. That means that, so we have to measure IRU super, super precisely if we want RU to not be hugely uncertain. Remember, this is the factor when we're doing uncertainty analysis. This is that theta factor, right? That we multiply when we have propagation of uncertainty. The propagation of uncertainty goes through this number. So that number is big. That is bad news. Essentially what it's saying is, oh, if you looked at the current here, and you looked at the resistance, they're related like this. And down here at low current, this slope is insane. So if you were to measure maybe like you have this interval of confidence in your measurement of the current. Let's follow that up and look what it looks like here in resistance. It's much larger, right? A little bit of error there becomes a much larger error a little bit of error in I becomes a huge error in R. And as you get smaller and smaller current, that problem gets worse and worse and worse. So this is really bad to measure low current, high resistance stuff. It's not great in any case, but it's really bad for that. So we try to avoid using this. And the same exact thing is true for this other case here for the voltage as well. So I'm not going to go through that one in as much detail, but essentially they're both super sensitive to the first measurement that you make, to the measurement of voltage or current, and that uncertainty propagates, and so our error is huge in the measurements. So there's a better circuit. Okay, there's a better circuit than just measuring the voltage and current through the resistor. There's a better circuit than using a voltage divider. So we'll learn that. And it's actually essentially two voltage dividers together. It's called the Wheatstone Bridge, and that's going to give us a lot better way to do it. So let's learn about the Wheatstone Bridge. The first thing to know about the Wheatstone Bridge is it's, to my knowledge, so bridge circuits in general, there are a few other bridges. You guys learned about diode bridges in your rectification lab, right? You guys went from AC to DC and you build a diode bridge. It's the similar bridge setup to that, except for its resistors. So the Wheatstone Bridge, and for some reason we like to draw bridges with 45-degree angles in circuits. I don't know why. People just like it. For some reason it's more fun that way, so we do it. So that is what we have here. The idea is we want to measure this unknown resistance, Ru, using this bridge that has a known input voltage, and we're going to find out that there are certain cases where you don't need to know the input voltage, which is kind of cool. Known output voltage, and known resistances R1, 2, and 3. Okay? So this is our Wheatstone Bridge, and we're going to do an analysis just like we did on the other circuits about what's the sensitivity of the circuit, see if we can get a feel for why this is the preferred method. Okay? So we would first like to derive the relationship between Vs and Vout. So when we analyze the circuit, we begin by just saying, what is the relationship between the input voltage and this output voltage? Notice that the output voltage is measured from this node here on this side of the circuit to this node on this side of the circuit. So that's the output voltage. The first observation we make is that the two arms of the bridge, which are R1 and R2, so R1, R2 is one branch, and then R3, RU is the other branch. So this arm, I guess, arm of the bridge, and then this arm of the bridge. So, you know how I think of it? It's like some guys like flexing. That. Arms coming together. These are the muscles.
Secondary muscles are the same
These
size.
are the elbows.
Same size as the other. So his arm's just a tube.
He's like Popeye kind of. Elbow,
All I know is that if that's the case, I
Elbow.
think I need to see a chiropractor.
and then legs.
Then arm should.
Yeah, he did skip leg day. Everybody skips leg day.
I didn't skip leg day.
What?
I skipped on like
Okay.
I just don't. If I just skip leg day, it's because I'm not working out. I never skip leg day.
Is that skipping if you just don't do it?
That's what I meant to say.
I think so,
That
yeah.
means you're playing constant.
So, yeah. here's our bridge. Now, we have these two arms, and each arm is a voltage divider, right? We have an input voltage Vs for both of the arms. And each of these has a series of resistors. So it goes R1, R2, there's a voltage divider, and then R3, RU, there's another voltage divider. So those are two voltage dividers in parallel. That's all a Wheatstone Bridge circuit is two voltage dividers in parallel. Okay? So that is, we can write the voltage across R2 and the voltage across RU using the voltage divider rule. So VR2 is equal to RU divided by R1, not RU. VR2, that's this one. R2 divided by R1 plus R2, right? So R2 and R1 are the voltage divider. So we want to know the voltage across R2. So VR2 is equal to R2 divided by the sum of them times the input voltage, which is Vs. Good old-fashioned voltage divider. Bam. The other side, the other arm, has VRU equals RU divided by R3 plus RU times Vs. So those are the two equations. Voltage divider equations. By Kirchhoff's law, voltage law, the output voltage is just VR2 minus VRU. If you wanted to, you could draw this sort of like imaginary element in here that goes from there to there, plus to minus. It drops that direction. So we could start at the tail, say, oh, that's just VR2 minus VRU. So I'm going to take that out so it doesn't look like I have put in an element there. So V out is equal to VR2 minus VRU. These yield the desired relationship. All we do then is just plug in V out is what we want, and we just plug in VR2 and VRU. We just solve for VR2 and VRU using voltage divider circuit. And if you're wondering, yes, this is the most elegant derivation of this equation I have ever seen. Yeah. It's actually much nicer than any of the other ones I've seen. I really don't know why they make it so complicated in the ones that I've seen, but they do. So, this is our output voltage in terms of our input voltage and the resistances. All right, so what we actually want to measure is RU, right? So stands to reason we would want to solve for it in this 6.2 equation. We know everything in this equation as long as we've measured it all. As long as we're measuring everything, we know everything in it except for RU. So if we solve for RU, we have what we want, which is this equation. What you see is surprisingly rare amount written down for whatever reason that is. I'll try to explain kind of why. 6.3, though, is actually a very useful equation, and if I was going to put a box around one of these equations, this would be the one. It tells you what your resistance, your unknown resistance is in terms of your other resistances and your two voltages, your input and output voltages. So if you have those measurements, you have a measurement for RU. So it's typically common or typical. I guess I couldn't decide. I just decided to put them both in, just for good measure. To have all resistors nearly equal to a single resistance R. Okay, so R1, R2, R3, and RU are typically equal to R. But then what RU is it's nominally R, but it's usually we say it's equal to R plus some delta R. some change, a little bit different than R. And we do the analysis with that. And actually, that's what I did when I derived the following sensitivities, but the delta R falls out from them. So that's why it doesn't show up. So under this condition, the sensitivities of the measurement can be found to be these three expressions. Now, I did derive these in terms of R1, R2, and R3 without assuming that they're all equal. And they're really gross looking, these expressions. So I didn't subject you to them. I made the assumption that they're all the same resistance. And this is what comes out instead. So these are our sensitivities. Now, it doesn't, I mean, just looking at these, so these are sensitivities for each of these values. So with respect to V out is probably the number one sensitivity we care about. This one's also interesting because we need to know what Vs is. We have to be able to know what our input voltage is, and also what is it with respect to R. It's not immediately obvious that this is a better situation than what we had up here, over here, right? So we said this is bad, but we're going to say this is good. And the reason we can say that is that, say our V out, for instance, if it got small, if our V out was small, which it actually often is, very small, you might say, well then, we have a small thing in the denominator going, being small again, that's squared, like that's bad news, right? It was over here, and then we had something small in the denominator that went to 0, squared. But notice that something shows up in the denominator with it. The Vs shows up in every one of these denominators.
So then it wouldn't matter if it's small.
So V out can be 0 if you want, and we still don't have this crazy sensitivity. So we can essentially control our sensitivity by changing Vs. So the greater Vs is, the greater this denominator is. So if you want to make your measurement less and less sensitive to variations in V out, Vs, and R, you can crank up Vs. Although it only really works to a point, because once V0 is much smaller, these essentially just drop out, right? Vs cancels. And you're left with sensitivities that are just like reasonable numbers, like 4R, right? So those are nice sensitivities.
On a side note, I don't think your motor's gonna make it.
Ah! Oh. We will see. It's going to be sketch. You're right. Challenge accepted. No, okay. So so essentially the sensitivity is good. If it gets to 5, I'm going to run to my office and get my cord. I don't want this thing to shut down on me. Okay, so now we have two methods of using this. So this is the analysis we're doing. I just hopefully have proved to you that we don't have the same sensitivity problem with the Wheatstone Bridge that we had with the other two methods of measuring resistance, okay? So that's good, but then the question is, so how do we go about actually making the measurement? The first one, the Null Method, is the one that you've probably heard talked about the most. And we will look at that. So the bridge is said to be balanced bridge, when the input voltage is not 0. So you put in some input voltage is not 0, but your output voltage is 0. Okay, so you put in some non-zero voltage and you get out 0. And so from this equation here, if you put in a non-zero Vs, but your output voltage is 0, which is to say these terms are 0, so these terms are 0, right? So that's what's happening. And then in this expression, if you're getting V out being 0 and Vs is not 0, that means that this term has to be 0, right? So we just say that R2 over R1 plus R2 has to be equal to RU divided by R3 plus RU. When this is true, we have a balanced bridge. From equation 6.3, V out being equal to 0 greatly simplifies the expression for the unknown resistance. So 6.3 is this one, right? So if V out is 0, these terms are 0. Vs cancels, and we're left with Ru being equal to R2, R3 divided by R1. Now, this is nice from an analytical point of view because a couple of reasons. It's completely independent of Vs, right? The Vs canceled, which is nice. So you can have you have 12 volts going in, 20 volts going in, doesn't matter. Your measurement, it comes out the same. You don't even have to know what it is. Well, you have to know that it's non-zero. If you're measuring 0 voltage out, it's good to check that you still have the source on. That's always good. But as long as you know you're not putting in 0 volts, you know that the bridge is balanced, and this is true. Of course, if Ru is a resistive sensor and its resistance changes such that the bridge is no longer balanced, the bridge must be rebalanced via changing another resistance, some known amount. Okay, so often R2, so it doesn't actually matter which other one it is, but often we choose R2 to be a potentiometer, which is drawn with an arrow through it. So a resistor with an arrow through it, which is all that means is a variable resistor. Potentiometer. So these can be like, have a little dial on it that you turn with your fingers. They're also often called pots. Potentiometer, POT, pots. Potentiometer. Little dial you can use, or it's a screwdriver you can use to turn the potentiometer to different resistances. Or they're also, like in the lab, we have these digital potentiometers, and you can change them using a microcontroller. So you can tell it, okay, change to this resistance or that resistance, and it will. Okay. Sometimes feedback control is used to maintain a balanced bridge. So you can have a potentiometer that's essentially in a feedback loop that is always rebalancing the bridge. So that would give you a way to make the measurement without having to manually adjust and balance the bridge yourself. So that is done. This is called the Null Method because it requires a balanced bridge or zero output voltage. It is difficult to measure a signal that is time varying unless it is slow with this method due to the required constant balancing of the bridge. So if you're measuring, like in the lab we were just doing, like this really fast time response, well, you're not going to have time. I mean, especially if it's like a manual potentiometer, you're not going to have time to move your potentiometer around and balance the bridge, right? So it's the same also with the thermal one. And actually, so the thermal one, I had you guys in the lab do this second method, deflection method. But when I first wrote that lab, I had you guys do it with the Null Method. And I had feedback on it, and I had a digital potentiometer that kept balancing the bridge. It was pretty fun. But then I was like, that's kind of silly. We don't need to do that. It was just more for fun than anything else. But the Null Method is used. It is kind of nice in some ways. It's really nice to have a really easy equation to have for your final result. But making that equation true all the time, but balancing the bridge can be kind of a pain. So the other method is called the deflection method. Oh, don't worry, I might just die. The deflection method simply lets the bridge become unbalanced, logs the data, and then applies equation 6.3 to compute RU. So it's like, well, it's nice when all this stuff cancels, but like also we could just measure it too and compute it. This is nice. So this is preferred for time-varying measurements for sure, because it doesn't require a much faster bridge balancing process to be happening simultaneously. It does require that VS is measured, which can, in some instances, lend a slight advantage to the null method in the case of stationary measurements. So it does make it so that you have to measure an additional quantity that you didn't have to measure before. But it has a lot of advantages. Dynamically, the Wheatstone Bridge is really nice because notice it only has resistors in it. That means that, in theory, it instantaneously responds to anything. So you change the input voltage, the output voltage changes instantaneously. So that's pretty cool. Of course, it's only approximately true. All right, so that is how to measure resistance well. And so resistive sensors, all of the resistive sensors, which is probably a class of maybe a quarter of all sensors out there, 25% or more of sensors that are out there are resistive sensors, you will virtually always put them in a Wheatstone bridge like this and use a Wheatstone bridge to measure the resistance. Okay? Look at this, 5%, nailed it. Yes.